Hello, I'm Dongkai Wang from Peking University. I'm glad to introduce our work 3D Human Mesh Recovery with Sequentially Global Rotation Estimation. This is a joint work with my advisor Professor Shiliang Zhang. This is the outline of this report. So let's start with introduction. In this work we focus on 3D Human Mesh Recovery, which aims to reconstruct human body mesh from an ocular input RGB image. And we follow the model-based human mesh recovery pipeline, which estimate parametric human model parameters, such as simple model, and then convert these parameters into human body mesh. So we take a look at simple model here briefly. Simple is proposed by Loper in 2015 and contains shape and pose parameters to generate human body mesh. The shape parameters are 10-dimension vector encoding the shape information of person, and pose parameters contains 24 predefined joint rotations along kinematics chains. Simple generates body mesh by 3 steps, namely shape blend, pose blend and skinning. A detailed introduction of Simple can be found in original paper. In this work we address the error accumulation of previous regression-based human mesh recovery methods. They directly estimate the relative rotation defined by Simple. However, to articulate the template mesh, relative rotation need to be transformed into global rotation along kinematics chain. This will lead to error accumulation that the error of parent joint will propagate to child rotation, causing large error at the end joints. So to address this issue, our motivation is to directly estimate the global rotation for each joint to avoid the transformation, therefore remove the error accumulation. So in this part I will give our method on global rotation estimation. In this work we propose a framework to directly estimate the global rotation of each joint to reconstruct human body mesh. And to relieve the difficulty of directly estimation, we propose 2 components to pursue better estimation results. The first is sequentially estimation. The motivation is that the rotation of each joint and its parent are highly correlated. From the statistic we can find that the relative rotation is small. Therefore we can adopt residual learning to rotation estimation to reduce the difficulty of directly estimation. Specifically, we take the parent joint rotation as starting point for child rotation optimization. This design can be benefited by the high correlating of parent joint rotation and produce accurate child rotation. Besides sequentially estimation, we also consider complementary feature to enhance global rotation estimation. Different from relative rotation that is determined by 2 body parts, the global rotation is determined by current part in image with template part in 3D space. So local visual clue is more important to global rotation estimation. Therefore we can cat a local feature with global feature to provide local visual clue. The next is experimental results. We test our method on widely used 3DPW dataset, and our method consistently improves the performance of a baseline method and ASO-TA method 3DCrowdNet. By replacing their relative estimation branch with our proposed SGRE, we can reduce the MSHP and PVE by a large margin. This improvement can also be observed in 2D human pose estimation benchmarks such as COCO and Crowd Pose. Finally, we provide some visualization results on 3DPW and COCO dataset with 3DCrowdNet. It can be observed that our method can reconstruct more accurate human body mesh from in the wild image. So in conclusion we propose SGRE to directly estimate global rotation of each joint to avoid the error accumulation of previous regression-based method. SGRE features a residual learning to relieve the difficulty of directly global rotation estimation and a local feature enhancement to pursue a better estimation result. And it achieves superior performance on 3D human mesh recovery and 2D pose estimation benchmarks. That's all. Thanks for your listening.